very abbreviated notation. We define u equal tau plus sigma and v equal tau minus sigma. And the periodicity condition of the total x gave us that x left, mu if you want, of u plus 2 pi minus x left mu of u was equal to x right mu of v minus x right mu of v minus 2 pi. So we spoke yesterday of the fact that the total coordinate, the sum of the waves that move to the left and waves that move to the right, is periodic, but that doesn't mean that the left waves and the right waves are periodic. They're almost periodic. Miss that thing. Now, we also mentioned quite clearly that u and v can be thought as independent variables, just like tau and sigma are independent variables. If you have independent variables and you have a left-hand side, a function of x, a right-hand side, a function of y, they're independent variables, well, the left-hand side cannot have x dependence and the right-hand side cannot have y dependence. So we basically can take a derivative, for example, with respect to u, a partial derivative with respect to u. We can vary u without varying v. And therefore, the left-hand side would give you the partial derivative of, with respect to u, would give you x mu prime L of u plus 2 pi minus x left mu prime of u equal 0, because you're taking a du derivative in this equation. And similarly, you can take a v derivative, a ddv, and you get that x right of u with respect to prime v minus x right mu prime of v minus 2 pi is equal to 0. So the x primes are periodic. The x's need not be periodic, but the x primes are periodic. That means we can write expressions for the x primes that are periodic, and we can invent the sum over oscillators. Now, we're already a little accustomed that this process of invention is done by writing something that eventually leads to nice constants. So let me write something that it's quite reasonable. X prime mu of u, we're going to write it as alpha prime over 2 square root, sum over all integers, alpha n mu e to the minus I n u. This is periodic in u, has the looks of derivative. Remember, our derivatives x dot plus minus x prime in the open string had that square root of 2 alpha prime. This is a little different. We'll see why. And sums over simple things. So this is also a derivative. So we've written something simple for it. And very soon we'll see it's the right thing to write. For the other one, for the x right, we'll write the following. X right mu prime of v, also square root of alpha prime over 2, sum over n over the integers, alpha n mu e to the minus I n v. But actually, if you see this, these two waves are totally independent. The oscillators shouldn't be the same. These are a new set of oscillators. We'll put a bar on the left ones. It's conventional. Some people put a tilde. I put a bar. Probably the tilde is eventually better, but bar is easier to write. So these are a set of independent oscillators. This is a set of independent oscillators. And they have some of the information. They implement this and that. Now, I want to integrate them because it's useful to see how this comes together. So let's integrate so that we find what is XL mu of u. And it's sort of easy to integrate. Each term we integrate it, and then we put some constants for a constant of integration. So there, when you integrate, you can have a constant. We'll call it x0 left mu. Now, this is the beginning of a story that repeats itself all over physics, and it has been used to death, even in the stuff having to do with amplitudes, is that closed string seems to be like a direct product of open strings. There's the alpha n oscillators that look like open string oscillators, and the alpha, well, the bars and the unbars here. So two copies of an open string content, and it's very fundamental. Now, when I integrate here, there's one term that is different, because I would have to put the 1 over n to integrate. Is the case of the zero mode. The zero mode gives you plus square root of alpha prime over 2 alpha 0 bar mu times u. When you differentiate with respect to u, you get the zero case in this equation. And then the rest of the terms, which require an I, square root of alpha prime over 2, the sum over all integers, 1 over n, alpha n bar mu, e to the minus I n u. So I integrated the first, and we can integrate the second now exactly in the same way. So this time we'll put an x0 right mu plus alpha prime over 2 alpha 0, no bar now, mu v, because we're doing derivatives with respect to v, and here exactly the same. I, or square root of alpha prime over 2, sum n belonging to z, 1 over n alpha n mu, e to the minus I n v. Yes?
Should the sum be n not equal to 0?
Yes, yes, thank you. N different from 0. Apologies, that's exactly right. Okay, now it, yes?
I'm sorry, did you repeat the what that alpha n bar? What is the connection between alpha and alpha?
There's no connection between alpha n bar and alpha n. They're independent. Mu, they're not the complex conjugates of each other, nor the Hermitian conjugates, nor anything. Totally independent. You know, classically, you should feel sure that that's true, because classical to quantum, the thing doesn't change that dramatically. Classical waves, you can have any wave going on one direction and a totally independent wave going in the other direction. So you should not expect any relation between them. Almost. Now, it really looks now that you've really doubled everything, which is probably quite strange. Alpha 0 in the open string used to be what? Momentum. Does the string have a left momentum and a right momentum that are different from each other? Center of mass. Does it have a left center of mass and a right center of mass? Space-time comes from this x0. Momentum comes from this, and these are excitations. So are there a double space-time because it's copies of two strings? Well, not yet. If you do T-duality and you make a dimension compact, yes, something like double space-time appears in string theory. But here, not yet. Why? Because it's time to go back to our constraint. We took the derivative, and we got an equation, but then we integrated. So we go back, and we see, oh, the failure of periodicity of XL must equal to the failure of periodicity of XR. Now, what is the failure of periodicity of XL? This is certainly periodic. And this is certainly periodic. This is not periodic. The failure of periodicity of XL is alpha 0 bar mu times this square root times 2 pi, because u plus 2 pi minus this. So from equation 1, this into 1 gives you that the left-hand side is just square root of alpha prime over 2 alpha 0 bar mu times 2 pi, which is the change of u. And for this one, it's the same. This is periodic. This is certainly periodic. And here you get square root of alpha prime over 2 alpha 0 mu 2 pi. And we obtain that alpha 0 mu bar is equal to alpha 0 mu. Just one momentum on the string. That periodicity condition that said that the waves going to the left and the waves going to the right are almost independent, but not quite, has constrained the two momenta to be the same. This is a crucial fact of closed string theory. Now, we're going to make a theory by combining this x left and x right. So let's look a little more at what is the total x. The total x of tau and sigma now is I'm sorry, here I put actually by convention a 1/2 and a 1/2. So it doesn't matter really, but let me keep the nice conventions. So x mu of tau and sigma is 1/2 x0 left mu plus x0 right mu plus. Now I have to sum, close the parenthesis, I have to sum these two terms with alpha 0 equal to alpha 0 bar. So let's put alpha 0. I have to sum the two of them, so I get the square root of 2 alpha prime. Alpha 0 mu, and then u plus v, which is u plus v, which is 2 tau. Now somehow, am I off by a factor of 2? I have in my notes just here a tau in here. This should be square root of alpha prime over 2 alpha 0, alpha 0 bar, alpha 0 plus alpha 0 bar, u plus v. No, it's not. That's the problem, I think. Yeah, that's right. There's no factor of 2. It's alpha 0 u plus alpha 0 bar v, which is square root of alpha prime over 2 alpha 0. And you factor it because it's the same, and u plus v is 2 tau. So it's correct. No problem. OK, false alarm. Here, plus I square root of alpha prime over 2, sum from n equal different from 0 to infinity, e to the minus in tau over n, alpha mu n e to the in sigma plus alpha n mu bar e to the minus in sigma. OK, that's how a full closed string coordinate looks like. We should identify alpha 0, which is equal to alpha 0 bar already, with the momentum of the string. And remember, the momentum density of the string is always p tau mu 1 over 2 pi alpha prime dx mu d tau. And therefore, the p mu is the interval from 0 to 2 pi of p tau mu the sigma, and that relates p mu to alpha 0. It comes to 2 over alpha prime alpha 0 mu. So this is the momentum up to a factor that is different from the factor for closed strings. The fact that these formulas have all these pi's different for open and closed strings and factors of 2, the pi's are always there. The factors of 2 are the problem. I personally don't remember any by heart. Just have to do it each time or look it up. This one, yeah, I tend to remember, but those square roots of alpha prime, hopeless. Anyway, look at this thing. You look at that string coordinate and you say a few things. First, lovely, you see those waves that are moving to the right here, and those waves that are moving to the left. Alpha, alpha, and bar double the set of oscillators of the open string. Alpha 0 has been reduced, and suddenly these two zero modes, you know, the only thing that appears in the dynamical variable of the theory is the average. So there's a momentum, so the momentum must be conjugate to the average position. There's no reason to keep the x at right because there's no two conjugates that I could possibly associate. So in the quantum theory, this is going to be replaced simply by x0 mu. You would do that in the classical theory as well. If the sum of these two things appear like that, that's it. So this is going to be x0 mu, the center of mass, and that's it. Okay, things to notice. You've been playing with orientation reversal in open strings. If you change sigma for minus sigma so that it runs in the other way, you change alpha n's with alpha n bars. So that's something to notice, for example. Okay, so I want to argue that these things have been written in such a way that things look good. So let's rewrite the fact that x, and I won't put the subscript mu, it's just too much work. X is equal to x left of tau plus sigma plus x right of tau minus sigma. So what is x dot? X dot is x left prime of tau plus sigma plus x right prime of tau minus sigma. You're differentiating with respect to tau, so the prime derivatives are the things that fall. What is x prime? Now, so small confusion. In the left-hand side, this x prime means the x with respect to sigma. And on the right, it means with respect to the arguments, of course, here. Anyway, with respect to sigma, you get xl prime of tau plus sigma. And here you get an extra sign because you have to then further differentiate the argument with respect to sigma. So you get minus x right prime tau minus sigma. So we get that x dot plus x prime, if you sum them, you get 2 xl prime of tau plus sigma. And that's the 2 that is responsible for this alpha prime over square root of 2 that we have there, because now this is square root of 2 alpha prime, sum over n, all n's, alpha n mu's, e to the minus in tau plus sigma. So x dot plus x prime looks exactly like in open string theory that we had this formula. And x dot minus x prime is 2x right prime. And it's for the left, I'm sorry, it's bars, 2 alpha prime, n belonging to z, alpha n mu, The mu's reappeared here for some reason, but it's okay. Tau minus sigma. So we've achieved that x dot plus x prime and x dot minus x prime look exactly like open strings with the same conventions and everything the way we said it. Still, the same commutator applies. We postulated for open strings that x mu of xi of tau and sigma with p tau j of tau and sigma prime was equal a delta function, I delta of sigma minus sigma prime eta ij. And the same is true for closed strings, these canonical commutation relations. Therefore, if the same commutation holds and the expansion has been organized the same way, you don't need to redo the calculations now, and you conclude that the alpha n bars and the alphas satisfy the same algebra of commutation relations that they did in the case of open strings. This is close to a proof the way I've stated it. If you want a little more details to make sure that everything really is in place, please read it up. But eventually, after a while, you get accustomed to these things. You just see that it's the same structure, so you take it and say, oh, the same thing holds. So this means that, moreover, in the open string case, we said that this combination with plus and the combination with minus commute with each other. There was a nice commutator between this combination and itself at different points and this combination and itself, but they commuted with each other. So the alpha n's and the alpha n bars really don't know about each other, and they commute with each other. So alpha n and alpha n bar are 0. So alpha m I alpha n j is equal to alpha bar m I alpha bar mj, and it's the same that you had in open strings, which is this commutation relation. If you want to put the square roots and relate it to a's, that's also possible. The formulas are identical, and as we said, the ones commute with the others. So alpha n I with alpha m bar j are equal to 0. So we're in good shape. Now you would say, all right, so after all, it's not all that different from closed strings. From open strings, I'm sorry. You've doubled everything, but then you discovered that the alpha zeros are not doubled. And there was an x0 left and an x0 right, but only the sum appears, so it's not doubled. The zero modes are not doubled. The oscillators are doubled, and that's pretty much the story. But as we will see in the light cone, this has really an implication that you maybe could not have expected. And there's going to be a constraint that shows up that it's a little baffling, and we'll deal with it. And that constraint is the origin of almost every difficulty that people have dealing with closed strings, the origin of almost every subtlety. And sometimes whenever people get stuck in a closed string calculation, they go back, it's probably something wrong with the constraint, because it's sort of very strange and fairly, not terribly strange, but it's surprising that you get into this kind of complication. So let me talk about Virasoro operators. Now, in the interest of time, I will not say too much about them, and you will play with them as well in the homework, but let's try to get the idea of what it is. You know, you have a coordinate x minus of tau and sigma. And this coordinate was supposed to be solved for, and it involves x0 minus a p minus, which is alpha 0 minus, and an alpha minus n, alpha n minus, I'm sorry, and all these oscillators of the minus coordinate, and then you'll have the alpha bar minus n. You see, just like any coordinate over there, x of tau and sigma, if you put for mu minus, well, you need an alpha 0 minus, and you need an alpha n minus, and an alpha bar n minus. Now, everything has been defined just like for open strings. And you remember it for open strings, alpha n minus was related to ln perp, was proportional to it, was another name for it. And this alpha bar n minus now is going to be ln perp bar. So the same formula you had for open strings for ln, you have it in terms of these are ln's that depend on alphas, and these ln bars just depend on alpha bars, but are exactly the same formulas as you had for open strings. So it seems like we're done. These are the Virasoro operators, how to get their formulas. And the formulas, I said, they come out exactly like for open strings because everything is done with proper conventions. So the only thing that is left over is this alpha 0 minus. What is alpha 0 minus? Which formula should I use? That is related to L0 perp. So should I use L0 perp or should I use L0 bar perp? It's almost like saying, should I use alpha 0 minus or should I use alpha 0 minus bar? And you say, but they are the same. What are you talking about? Well, they should be the same, but they're not the same. You see, the formulas, everything has been done exactly the same as for open strings. So here, in this formula, in order to define Virasoro operators, you sort of square this and relate it. You're going to have the alpha bars, and here the alphas. So if you tell me that alpha 0 minus should be equal to alpha bar 0 minus, that's okay, but we have formulas for them. So L0 perp is going to be, as you probably remember, it's something with the momentum. In the case of the open string, you just had alpha prime pi. Here you have a factor of 2. For the zero modes, the factors of 2, I'm sorry, there's no way to get them to be the same. But then we had plus this sum over p, say 1 to infinity, alpha, the distraction operator here, p, I, alpha minus pi. That was L0 perp. But now you have L0 bar perp equal alpha prime over 4 pi plus sum from p equals 1 to infinity, alpha minus pi bar, alpha pi bar. And this operator looks completely different from the first operator. This involves these oscillators, the right movers. This involves the left movers. This is L0, the formula for L0, and this is L0 perp. This whole formula, if you remember, comes from L0 equal 1/2 sum over p, alpha minus p, alpha p over all integers, and then you have to reorder, you get to throw the infinity, and you get this term, and you get the zero modes, and That's where it came from. But now you have this thing over here, and you need them to be equal to each other. So how can they be equal? They look so different. Whenever we had a constraint, say in the light cone, we had the Virasoro constraints, and we solved them all by setting x minus equal to things. So can we solve this constraint, that this should be equal? No, it's unsolvable. There's no way to eliminate some degree of freedom of the closed string and make this constraint look. So the only thing we can do with the statement that these two should be the same, alpha 0 minus equal alpha bar 0 minus, is to demand that L0 perp minus L0 bar perp is 0 acting on any closed string state. So whenever you write what you think is a closed string state, it's going to be the vacuum acted by some alpha bars. It may not be a closed string state. You better make sure that it satisfies this constraint. So this is an unsolvable constraint. The light cone was the nice thing in which everything was physical, and you could build states and everything there. When you work classically, you specify any transverse motion, xi's, and you could construct x minus, and everything was fine. But for the closed string, just like you saw in one problem, there's always a subtlety, and this must be imposed on the closed string state. So L0 here, written this way, is equal to alpha prime over 4 pi plus the number operator, perp, and the alpha prime over 4 pi times the barred number operator. So this thing is equivalent to saying that the n minus n perp bar also kills the states. Normal ordering. Well, we believe in this trick that when we had to reorder things in L0, we get this minus 112 for each coordinate. So what's going to happen? Wherever we had an L0, we're going to get L0 minus 1. L0 perp, you'll get L0 minus 1 as well in the quantum theory. So let me write it like this. Square root of 2 alpha prime alpha 0 minus is equal to 2 over p plus L0 perp minus 1. And if you do the barred one, it's everything with barred. So what people do is they say, well, to take it like this, 1 over 2p plus, 1 over p plus, I'm sorry, and put instead of this, instead of L0 perp, put 1/2 of L0 perp plus L0 bar perp to make it symmetric, because they're equal. So you put L0 perp plus L0 bar perp. This gives you twice this, and the 2 is here, minus 2. So that's the same formula. And this thing is alpha prime p minus. I'm putting all these alpha primes here, but basically the only thing I want to get back to you is that things are the natural extensions of open strings, so I will not bother you anymore. H in open strings was L0. Here is L0 plus L0 bar minus 2. And the mass squared formula, it comes from m squared is equal to minus p squared, as usual, 2p plus p minus minus pi squared. Go through the steps. The mass formula is 2 over alpha prime n plus n bar minus 2. So basically, if you need more conventions, look them up. But this is the whole story, and it's intuitively clear. In the light cone, you get two types of Virasoros, and even L0 looks different from L0 bar. Therefore, there's a non-trivial constraint, and here it is. Now, if you want to interpret this constraint better, you can think of what it does. And there's a nice physical interpretation. What is L0 plus L0 bar perp? This is basically up to a number proportional to the Hamiltonian. And therefore, it generates time evolution. From the Heisenberg equations of motion of the Hamiltonian, which is this operator, this thing generates, we said Virasoros generate reparameterizations. So L0 plus L0 bar generates tau translations. That's its job in life. So what is L0 minus L0 bar? With an exercise you will do today in the tutorial, you'll be able to show that L0 minus L0 bar, that's a very lovely thing. It produces dxi d sigma. Instead of tau translations, it produces sigma translations. L0 minus L0 bar is the generator of sigma translations. What is it saying? The statement that this L0 minus L0 bar generates sigma translations, but it kills all states. It states that all physical states are invariant under sigma, constant sigma translations. It's that universal fact that there's nobody in this planet that has figured out how to select a special point in a closed string. Where sigma equals 0 is in a closed string has been impossible to determine. Nobody can determine it. And there's a reparameterization that cannot be taken care of by solving something. So all strings can be changed. Once we fix sigma, you can change all the sigma lines that are here on a string. You can rotate them all. And that's this constraint, L0 minus L0 bar. People say L0 plus L0 bar is dd tau, so it's energy in the two-dimensional world. L0 minus L0 bar generates sigma translation, so it's momentum generator in the world sheet. Nothing to do with momentum in space-time. Momentum in space-time is p mu. Momentum in the world sheet is a generator that generates sigma translation. So L0 minus L0 bar is world sheet momentum. At the end of the day, all states of the closed string must have 0 world sheet momentum. So state space. All right, how do we write general states in this theory? I want to say one thing first before we start with our states. Remind you of what states we had from your experience with light cone. Your experience with light cone fields, you obtain states of the form ij, psi ij, AP plus P transpose IJ dagger on the vacuum. And when psi ij were symmetric, traceless, these were graviton states. And when they were antisymmetric, which was a problem you did, these were Kalb-Ramond states. And those corresponded to the B mu nu field, and this for the metric H mu nu field. So let's see what we get from the closed string. What is there in the spectrum of closed strings? All right, so the general state. Now this is a formula that it looks formal, but if you can write it, it means you understand how you're building states. So again, there's ground states. P plus and P transpose, like for open strings, ground states. And we'll build the general state, lambda and lambda bar, from this ground state. So we have to put all types of alpha n oscillators. So we'll put ANs from n equal 1 to infinity, from I equal 2 to d minus 2, no, to d minus 1. Space-time dimension minus 1, and you put A's, N's, I's, daggers to the lambda n I. These are creation and annihilation operators normalized to 1. Nevertheless, the number, they contribute to the number operator n, not 1. Then for the bars, you have a totally analogous sum. M equals 1 to infinity, J equal 2 to D minus 1, A, M, bar, J, dagger, to the lambda bar, M, J, close the parentheses, and then you put P plus P transpose. So you need to put everything there. Every oscillator can appear and can appear a number of times. So there's going to be, if there was infinite for open string, this is like infinite squared. Now, you must have that n perp. How much is it? Let's count the number here. Each of these oscillators gives n, but there are lambda ni of them. So this is the sum over n and I of n times lambda ni. And that somehow, when you build it, you can put all kinds of things here and all kinds of things here. But the total number from these oscillators, right-moving oscillators, must be equal to the total number from the left-moving oscillator. So this must be equal. Well, I'll write the n bar perp is the sum over n and I again. N lambda bar n I. I don't have to use j's there. And of course, these two numbers must be the same. So let's begin to build the states. Lowest states, n perp equal n bar perp equals 0. So it's just the ground states. How much is the m squared? Well, the formula is there to the left. Is n is equal to n bar equals 0. So this is minus 4 over alpha prime. And these are the states that we know are associated to a scalar field. So this is a scalar field that is a tachyon. A tachyon, again, because the mass squared is negative. So it's some sort of instability again. So we said that the open string tachyon was a sign of instability of the D brane. So this is a closed string tachyon. What instability is it associated to? Can anyone tell me? Now, this theory has been around 25 years that people discovered that tachyon. Of course, only in 2000 people understood that the instability of the open string tachyon is instability of D brane. So what is unstable in the closed string? Have anybody heard even anybody say what's unstable here? A talk, a colloquium, anybody? No? Good. Nobody knows. It's a funny thing. Probably the day anybody will figure this out will be considered a big discovery. We suspect what it is, and there's some evidence of what it is. This is very dramatic. This closed string has gravity and all that. This tachyon probably is the instability of space-time itself. Just like a D brane decays, in this closed string theory, space-time can annihilate itself and disappear. And it's probably true that it does that. So somehow this theory has the ability maybe of, through a tachyon fluctuation, create the space-time and then destroy it again. The problem is that nobody has been able to calculate the tachyon potential. We've tried quite a bit. I myself have tried a bit. And sort of it seems to suggest that that happens. You see, the tachyon field is a field that sort of makes strings very heavy. And sort of as the tachyon field develops in the open strings can't move, can't do anything. They become closed strings and suddenly. So this tachyon field seems to do the same thing. It freezes out everything. It freezes out even gravity. Freezes out the full closed string. When you freeze out gravity, you probably destroy space-time. Because there's not anymore a dynamics of space-time. So, you know, this problem will be solved, I presume, the next decade. Somebody will figure it out. But we don't know the answer. Yes? Well, the potential of the tachyon is something that we can't access with these calculations because basically potentials, you see it in a field theory if you write a Lagrangian. So you need to write a Lagrangian for this tachyon. For the open string, people could calculate it. It was very difficult, but it could calculate it. But you need the string field theory. You also have a string field theory for closed strings. But it's non-polynomial, just like Einstein's gravity is non-polynomial. So the calculations are even more difficult. And nobody has quite identified the tachyon potential. Might be that the potential doesn't have a critical point. The open string tachyon had a critical point where the D brane decayed. But if space-time decays, maybe it has no critical point. Nobody can calculate it yet. Anyway, so we'll leave that one, mysterious tachyon, and go on. So next level, n perp equal 1. But if n perp is equal to 1, n bar perp must be equal to 1. And as nice result, m squared is equal to 0. So here we go, massless states. What are they? Wonderful. That's what we wanted. So we can put an A1 I dagger, and we can put an we must put, to satisfy the constraint, an A1 bar J dagger. I and J need not be the same. You need, the number here is 1 for the left, for the right mover. Here's 1 for the left mover. So this is fine. And you can put anything here. Let me call it Rij, any set of numbers, and P plus P transpose. These are the collection of states at mass squared equals 0. Now, Rij as being any arbitrary two-index object, because there's no more constraints. Rij is totally arbitrary, has a symmetric part, Sij, and an anti-symmetric part, Aij, symmetric and anti-symmetric. Moreover, has a symmetric traceless part. You take out the trace from Sij, and then you add it back, so plus some contraction, S prime, I will call it, times delta Ij. I could tell you what these things are in terms of Sij, but I don't think it's really necessary. You know that any symmetric object can be written as a symmetric traceless plus the trace, plus Aij. So actually, we have three types of states here. These are linearly independent combinations of states that transform separately under the action of the Lorentz group. The symmetric traceless part transforms among themselves. The anti-symmetric objects transform among themselves in the Lorentz group, and this one. So here we have symmetric traceless Ij, A1 I dagger, A1 bar J dagger on P plus P transpose. What are those? Look there. This looks exactly analogous to those massless states. They have P plus P transpose. They have I and J polarizations. And they're massless. And they're accompanied, for the case of the graviton, by a symmetric traceless matrix. So these are graviton states. This is the moment where gravity emerges in closed string theory. It's sort of a little anticlimactic because it appears so easily. You just build those states, and there it is. Symmetric traceless combinations, massless states, Ij indices of polarization. That's it. The Aij's, A1 I dagger, A1 bar J dagger, P plus P transpose, well, they are the Kalb-Ramond states. So not only you have gravity, you have a Kalb-Ramond field, and then the last one, you put this thing in here, and you get S prime, one state only, delta Ij traces this thing, so A1 I dagger, A1 bar I dagger on P plus P transpose. The I is summed here, so it's just one state. So it's as if there's no index here, and if there's no transverse index, this is a scalar field. It doesn't transform under Lorentz transformation, and this is called the dilaton. It's a scalar. Yes?
Apart from mass, what other differences characterize the massive graviton states from the open string and this mass?
It's the mass. And, well, no, the massive graviton of open string theory is a symmetric traceless tensor in D minus 1 dimensions. And the graviton, the masses is in D minus 2 dimensions. You see, a massive vector has D minus 1 components. You probably have done that in the homework when you did the massive vector. All massive particles are representations of SOD minus 1, while massless are representations of SOD minus 2. So that's the difference. You could have a whole course on each one of these three fields. Gravity field, this. Kalb-Ramond field has to do with the charge of string theory. Strings are charged, and the Kalb-Ramond field is the one that responds to its charge. Between the two fields, you have the symmetric and antisymmetric parts of a matrix, mathematicians have invented what is called generalized geometry that puts these two fields sort of in the same footing, gravity and antisymmetric field. It's a lovely area of research. The dilaton is another big story. It controls the strength of the coupling constant in string theory. It's a very subtle field because it's a field that controls the coupling. So its properties are extremely unusual. It's very interesting. So in the last minutes, we're going to introduce what we're going to do next time. And it's we're going to apply one of the things you guys have learned about. We're going to do an orbifold, and we're going to solve it completely. So which orbifold and how are we going to solve it? We're going to do a simple orbifold. And we're going to solve it, a closed string orbifold. So closed strings on R1 over Z2. What was R1 over Z2? Was the real line you let x equal to minus x, so it's half the line. Now, strings live in many dimensions, so you're going to do the orbifold in just one dimension. You're going to take one of the many spatial dimensions of string theory and just orbifold in one. Yes? Yes. Yeah, well, indeed, we have identified linearized gravitons. So you can ask whether you identify gravitons all the way, non-linear gravitons. In fact, there's all kinds of theorems in particle physics that you have linearized gravitons with linearized gauge invariances, it fixes uniquely the interactions. So once you get linearized gravity, you must get all of gravity. So if interactions can be defined here in this theory, you must get them. So indeed, that's true. So here we're going to take all the, remember, what are all the coordinates of string theory? You have x plus, you have x minus, you have xi. Well, let's split the xi's into x little i's and x, which is going to be like x25 that we're going to call x. And that x25, which we call x, is going to be the one we're going to orbifold, so that by the time you do the identification, you have just half the line. This is x25, which is equal to x, and that's orbifolded. The other dimensions exist forever. Now you're going to say, oh, terrible, general relativity, a boundary. I'm going to have to put boundary conditions here and boundary conditions there. And how am I going to know that this is consistent? We'll look at the adjoint Hamiltonians. Nothing of that happens. It's much easier than that in string theory. In string theory, we proceed in the following way. We construct an operator that produces this transformation. So this operator is going to be called U. And U is going to take x of tau and sigma and give you minus x of tau and sigma, for x being x25. And U should take xi of tau and sigma and do nothing to it, because the other coordinates are not orbifolded. And U should take p plus and x0 minus, which have things to do with the first dimensions, and do nothing to them as well, p plus x0 minus. Okay. Now you can ask yourselves, if U is an operator that implements the orbifold identification operator, implementing the orbifold. What does it do to x minus? Well, it doesn't do anything to its zero mode by definition. It probably shouldn't do anything to it. And the reason it doesn't do anything to x minus, so u x minus of tau and sigma, u, we claim, is x minus of tau and sigma. It's because x minus is determined by x0 minus, p minus, and the alpha n minuses. P minus is related to L0 is a Virasoro, alpha n minus is a Virasoro. All Virasoros are products alpha I, and n, and you sum over all i's. So you sum over all little i's, and you sum over x25. But x25, when this is 25, appears squared. So if the x25s are changed sign, when they're changed sign twice, it doesn't matter. So x minus is an invariance. It's invariant under the orbifold identification. And therefore, under the orbifold identification, you also have that h equal alpha prime. P plus P minus is invariant. U, H, U is equal to H. So it's a symmetry of the theory. And we can restrict states to this symmetry. I'll do 3 more minutes and leave it there so that we'll finish it tomorrow. Tomorrow we also start superstrings. So just a couple more comments. We are going to what you do with orientation, we're going to do here. We're going to say the states of the orbifold theory are the states that are invariant under the action of U. Just like we said, orientation invariant states are the ones that are unchanged if you do the orientation reversal. In this theory, we're going to have the intuition that we're going to apply to all possible states of the original theory, what people call the parent theory. We look at what states are invariant under U, and those are the ones we keep. U essentially relates what happens at minus x to what happens at x, because it moves that. So those states that we keep basically encode on this side of the line all the information of the states everywhere. So it really is some sort of truncation of the space, as we'll see right now. So 2 more things. We'll truncate to U invariant states. And one last thing, we had our closed string expansion, x0 plus alpha prime p tau. This is all x25. When I don't put an index now, is x25. Is our orbifolded one. Alpha prime over 2, sum e to the minus I n tau over n, alpha n e to the I n sigma plus alpha bar n e to the minus I n sigma. Well, if U does this, it's clear that U acting on x0 should give you minus x0. Because if U acting on this is supposed to give you minus x, the operator here is x0. Here is p, so acting on p must give you minus p. Acting on alpha n has to give you minus alpha n. And acting on alpha n bar is going to give you minus alpha n bar. So this is going to help us construct states invariant. Like you can have, when you build an arbitrary state, you can use some oscillators from this dimension, the 25th dimension, and some oscillators from the other dimensions. But then you must use an even number of oscillators from this dimension. And actually, it's a little more intricate than that, as we will see, because the ground states are also not invariant under the orbifold transformation. Remember, the P plus, P transpose, P transverse is now P plus, Pi, and P, because there's the normal and the 25th. And the orbifold changes P to minus P. So these ground states are not invariant. So you're going to have to take linear combinations that make it invariant. And it's going to be a fun thing to just construct this whole thing. So we'll do that tomorrow for about half the lecture. And then we begin superstrings. All right. That's it. Because people do compactification. Have an action and start reducing over the space and doing all kind of boundary conditions and tremendously complicated things. It's just imposing the action of the orbifold transformation that does everything. It's